share the screen. So let me figure out which. Okay, this is the moon, the lunar one. So is it okay to start with lunar?
Yep.
Yeah.
Ladies and gentlemen?
Yep.
Okay. So I guess I'll put it in present mode. And all right. So why don't you guys introduce yourselves?
I'm Mason.
I'm Jordan. And I'm Zara.
Mr. Shaner, can you hear them or do they need to use the microphone? Because I do have a microphone.
I can hear him just fine.
Okay. All right. This beautiful picture of the moon is courtesy of Mason.
And this is my picture because I'm going to be starting off. If you could go to the next slide, please. So I actually found something really interesting. I was trying to come up with another slide because I felt like my moon slides were a little lacking. And I ended up actually finding out that this picture was of the Apollo 12 landing site. I had to examine it pretty closely, but one of the main things that helped me figure it out that it was the Apollo 12 site was the triangular pattern of the 3 craters that I outlined in both images. And I also labeled some of the other features in the other image that I actually used to figure out the Apollo 12 site. Next slide, please. And this is the annotated version of the picture. As you can see, there's not a lot of complex craters, but there's quite a few simple craters. And a note for the next slide is that this entire image takes place on a mare.
Is that okay?
Yeah. So the 3 geological features, as mentioned before, were mare, simple craters, and complex craters. The main thing between simple and complex craters is that simple craters are normally less than 15 kilometers in diameter and don't have the energy required to do a lot of displacement. And they tend to leave a more bowl-like crater compared to complex craters' more flat surface. And mare are low spots and dark spots on the moon that formed because of the lunar cataclysm over the period of 4.1 and 3.9 billion years ago. Generally speaking, the complex craters are older than the simple craters because you can't crater inside of something unless it's there. And the mare are older than complex craters because the complex craters can't crater inside the mare if it doesn't exist.
Okay. All right.
Okay, so this is my photo. You can go to the next slide.
Mhm.
So I noticed that there was a wrinkle ridge in the middle of the image, and that was the main geological feature that I noticed. There's also a complex crater on the right that I noticed, but Mason had already talked a lot about the complex craters, so I mainly wanted to focus on the wrinkle ridge, as well as the rills that are kind of in the shadow or underneath the wrinkle ridge on the left side. If you want to go to it. So, like I said, there is a wrinkle ridge in the middle of the photo, which is basically a long curved feature that's raised out of the ground. And there are rills in the groove and some smaller complex craters on the right. And just like Mason said, complex craters are formed by a high velocity object that impacts the surface. And since the objects are large, they have the energy to modify the surface of the moon, which leaves craters with flatter surfaces. The wrinkle ridge, which is the main focus of the image, was formed when the basins were flooded with lava and then they contracted. So after they contracted, the basalt lava broke and flooded, which created the wrinkle ridge as well as the rills underneath. And the wrinkle ridges are low, sinuous ridges that are formed on the mare surface. And I learned that they can extend for up to several hundred kilometers. But I noticed that the scale on my image wasn't that great, but it was only a portion of the image, the ridge that was shown. So it's hard to tell how long it could have been. So The rills were formed by a collapse of surface materials or collapsed lava flows, or like you can think of it as lava tubes. And the difference between the wrinkle ridges and the rills are that when the lava contracted, it creates the actual ridge sort of shape. So it's like, since the moon doesn't have tectonic plates, that's what creates the tectonic features on the moon. And then the rills are obviously formed by something collapsing. I learned that the complex craters are likely older than the ridge due to the darker coloring that I noticed. And it's hard to tell the age of the wrinkle ridges because there's so much ongoing research in the field, and scientists don't really know that much about how to tell the ages of wrinkle ridges. But I assumed that the complex crater was likely older than the ridge.
All right.
Okay, so this one is my image. It's a little bit different because the scale is a lot larger. So if you look in the reference on the bottom left, it's actually 22.8 kilometers long. And in the image, if you go to the next slide, I've pointed out some of the major features. The one that's the red circle is the Apennine mountain range. There's a blue circle where there's a pretty large impact crater. There's a sinuous rill that runs through the majority of the image, and then all the way on the left side is the Imbrium Basin. Okay, so first to go over some of these features, one of the most prominent in the image is definitely the sinuous rill that was pointed out in the center. And through further research, I found out that it's called the Hadley Rill. So in general, rills are long, narrow channels formed by volcanic activity. And I tried to approximate the best that I could. It's around 70 kilometers in length of just what's shown on the image. And this length is pretty typical for rim, which could even be hundreds of kilometers long. And another prominent feature is the Apennine mountain range. These are special because they're fault block mountains, and they're informally referred to as the Swan Range. And finally, the western side of the image is the Imbrium Basin, which is an example of Mare formed by an impact. There's a deep impact crater on the side of the Hadley Rill as well. There were others in the image, but that was definitely the largest one. So about how they formed, the sinuous rill meanders. I like to think of it like a river, like rivers meander by going back and forth, and the sinuous rill is really similar to that. This is because they are thought to be collapsed lava tubes or lava flows. The reason that fault block mountains, like the Apennine Mountains, are formed is the result of an impact that the same one that formed the Mare Imbrium. The Imbrium Basin, as I said, formed through collisions with asteroid-sized bodies. So about their ages, impact basins formed between 3.9 and 3.7 around billion years ago, but most basins filled with debris, leaving them flatter than they were originally. So based on the image, I'm not 100% sure, but just based on the image, I think that the impact crater shown is likely much younger, since if the largest basin filled with debris over time, the impact crater would have filled as well. So I think that's showing its young age. In addition, the Hadley Rill would have been destroyed by the impact that formed the Imbrium Basin if it was older, so therefore it's likely younger than the basin as well.
I think, oh, sorry.
So through further research, I found some additional images, and I found out that this is actually the landing site of the Apollo 15 mission. The first image is a photo from the mission of the Hadley Apennine site, And there's also an image in the middle of the Swan Range from the surface itself. So you can see their scale, they're pretty tall. And there's the module Falcon in the front. And the final image is a more zoomed out shot showing the highlands versus the Mare Basin. You can see the light versus dark in the image. And yeah,
Is that the last slide?
yeah, I believe that's the last slide.
Okay.
Okay. Thank you. So this is great. So yeah, I've never seen that picture on the right before. Oh, that's pretty cool. It's just a different way of seeing that area than I've typically seen. So that's pretty cool. Okay, great. Go on up to the picture. Go up or back a slide, whatever.
Sure.
Which is slide to image 3.
Image 3, this one? Or
Yeah,
the,
there you go.
no,
Okay.
this one?
Yeah, that's fine. Yeah. So yeah, so good job characterizing this. Question for you, and you can take a second to think about it. Considering, because there's 4 main, as you point out, there's 4 main geologic things you can see in this image: the highlands, the mare, the rill, and lots of craters, but most prominently Hadley crater, that larger one there, right kind of in the middle. Can you rank for me their relative ages from oldest to youngest? So those 4 things, from oldest to youngest: Mare, the crater, the rill, and the highlands. Do you understand my question?
Yeah, I understand your question.
Okay.
From oldest to youngest, I believe that from oldest to youngest, it would be the highlands, Mare, the rill, and the impact crater. I'm not really sure, but I think that's what the order would be.
Okay. Do either of your colleagues want to challenge that, or do you agree?
I agree.
That's right. You're right. Yeah, very good. Very good. Okay. Yeah, this is one of my favorite one of my favorite pictures of the moon, just because there's so much going on here in terms of geology. It's also pretty cool to see Apollo 15 landing site is, well, it's in that picture, which is neat. If you haven't seen it yet or before, do a search for, like, in YouTube, the Apollo 15 hammer and feather experiment. Have you seen this?
No, we haven't.
Okay, check it out. It's pretty cool. So in Apollo 15, so as you pointed out, the lander was called the Falcon, right? So they took a falcon feather with them, and they talk about this in the video. It's pretty short. They took a feather and one of the rock hammers they had with them, one of their tools, and they were going to test out Galileo's idea that things all fall at the same rate in a vacuum. So astronaut, his name was Dave Scott, he held up this feather and this hammer at the same distance, and he let go to test out this idea. So go watch the video and go find it and see what happens. Pretty cool. It's probably maybe a minute long, so it's pretty short. It's pretty cool.
I've got the link to them, so I'll give it to them.
Okay, cool. Great. One comment I have just on all your, well, not all your slides, but where you did this in a few places. So if you go to the next slide.
Go to the next slide, this one?
Then one more.
One more, sorry.
There you go. So don't do this. Don't put a slide up that's full of text like this. I mean, I understand why, right? It's kind of their prompts for you for your discussion. But you can easily just like print that off.
Okay.
Or if you're using like if you have a dual screen setup, you can put them in the notes section for your slide, and you can put those on a separate screen. But in general, when you're presenting, you don't want to have, you really want to minimize the amount of text you have on a slide. And the reason is, if you have a lot of text on your slide, or any text you have, any text, doesn't matter how much you have, any text you have on your slide, that's what people's on the audience, that's what they're drawn to. So if you have a lot of text, they're going to spend more time reading your text and not listening to you. So if you have something important to say that's not up there in the text, or let's say you get to it and they're still reading the text while you go on to the next slide, they're going to miss that. What it was, the important thing was that you had important points you had to make. So just for the future, you don't want a lot of text. I mean, sometimes you need to have text. I mean, I'm not saying no text. I'm not daring you to do that. But just really minimize the text that you have. And I will say that professional scientists are guilty of doing this, especially when you see their conclusion slides. They'll have like, 10 bullet points of like they're saying, here's what the point is. And it's like, okay, a little unnecessary, dude. So just something to keep in mind. Go to the second picture.
Okay.
There you go. Okay. So you said this was a wrinkle ridge, and you said there were some rills. Can you point the rills out to me?
If you go to the next one, then
Oh, yeah, take it.
Backwards. My fault.
yeah.
Is that the one you want me to go to?
Let's see your second. Okay. Okay, so this is a very difficult image to try to characterize because the sun angle is very, very high, meaning the sun is not completely overhead, but pretty darn close. So there's not a lot of shadows, as you could probably tell, right? So without really having shadows, it's really hard to tell what things are you're looking at. In this case, the feature you see running down the middle that you identify as a wrinkle ridge, that's actually a rill. That's a single rill. So you're looking at a depression rather than something elevated.
Uh-huh.
Can you see that now that I've said that?
Yeah, I did.
Yeah, because sometimes you just can't see it, right? Because you don't know what it is, because of the shadows, right? Lack of shadows. So let's look at a rill, and go to the next. Go to that third image, and just with the image itself. There. Okay. You see that elbow there, that bend in the rill near the top, what's near the Apollo 15 landing site. Okay, that's that same elbow you see in that rill in the other picture. So image 2 is zoomed in on that particular part of Hadley Rill. So the Apollo 15 landing site is kind of just off the picture, off the frame to the right, not too far from that. So this is a rill the astronauts went to and visited up to the edge and took pictures of it. It's big. It's really big. It's really deep. It doesn't. It counts like a crack. Well, it's a lot bigger than a river. Let's put it that way. It's pretty big. It's pretty big. I have. Okay, and let's go to the first picture. Oh, real quick, I will say, yeah. So those are craters. All those circular things you see in that image are craters. They don't look particularly circular, again, because of the really high sun angle. So if you see this picture at a lower sun angle, a lot of these things are a lot more circular and look like the way they should look. Okay.
Thank you for that. I did not take into account the sun angle.
Well, I didn't tell you either, right? I didn't give you the sun angle or even the direction the sun was coming from in these pictures. I did that on purpose. I just want to see what you all come up with.
Okay.
All right, let's go ahead and go to the clean one, so to speak. Okay, so I thought that was kind of cool how you like kind of triangulated. And it's funny because like I never really looked at it like that way before, but since you pointed it out, I'm like, oh yeah, look at that. If you use those particular craters, there's a triangle. So this is, as you identified, the Apollo 12 landing site. Although, to be honest, this picture is actually flipped from from the actual original image. So in the original image, the landing site and the lander, that crater all over on the left side of the picture. So I flipped it around on purpose just to try to kind of throw you off so you wouldn't notice the lander. But few people notice it. Few people pick it up. You did. So good job with that. So what's cool to point out is obviously the lander's there still, or it's just the bottom half of the lander. I should say the top half is what put them back into orbit around the moon. But all those dark linear streaks you see extending away from the lander, that's their astronaut footprints. It's where they disturbed the regolith as they were walking along. And they also had this cart, it's like a two-wheeled cart that they used to drag along tools and things with them that they were using. So it's kind of a combination of wheel tracks and their footprints. So that's pretty neat. And you point out the Surveyor 3 lander that landed there about 2 years before that, I think. And they actually went over and took a piece of metal off that lander, off that spacecraft, and brought it back for engineers and scientists to study to see, what happens to something like that being exposed to solar radiation for 2 years unprotected. Because at that time, we didn't know. We had no idea what solar radiation does to objects like that. So anyway, I will tell you, every crater in this picture, and there's a lot of them, every crater in this picture is a simple crater. There are no complex craters in this image. Some of them are very, very, very old, or like you really can hardly tell they're there anymore, because they've been filled in over time by other impacts throwing debris in. But they are all sitting on Mare. This is a Mare section. I don't remember. I don't think the specific point was in your readings, but every solid surface, so every object like the moon, the Earth, Mars, Mercury, every solid object in the solar system, every object that has a solid surface has what's called a transition diameter for craters. And what that is, it's a range of sizes where you stop seeing simple craters and you start seeing complex craters. For the moon, that diameter is about 15 to 20 kilometers. So based on the scale bar here, none of these things, based on that one fact, none of these things here can be a complex crater. They're just way too small. But other than that, they don't really exhibit features, characteristics of a complex crater. So, but anyway, as you correctly identified, they are mostly simple craters. Some are younger, some are older. You can tell just because the older ones are really filled in a lot. Like for example, the crater, the rim that Apollo 12 sits on, that's obviously much older than like the little bigger one is kind of to the lower left of it. That's much more of a bowl shape. It obviously is not as filled in. There's also something called regolith maturation, something like that, where the longer, if you have a regolith soil dirt that's brighter in color, over time it will darken with exposure to the solar wind. That can also be an indicator of how old something is. So, yeah, that's pretty much all I had. Otherwise, overall, good job. So whenever you're ready, you can go ahead and bring up your asteroid slides. Just curious, how much time do we have?
Another about a half hour or so.
Oh,
3:18.
plenty of time. Plenty of time.
Yeah, I thought it was a good amount of time. All right. Oh, you guys, I'm not sharing this with you. I'm sorry. I unshared. I forgot that I did that. My bad. Sorry about that. Nope. Okay. My apologies.
Okay, so I had the first asteroid picture, and we did further research, and I found that this asteroid is actually called Itokawa. I'm not actually sure how you pronounce it, but I'm pretty sure it's Itokawa. If you want to go to the next slide, then I can show it. So I saw that there were two main bodies of Itokawa, and that made me think about how it was formed, probably through accretion, where the two main bodies came together. I noticed a lot of different boulders, and there were a lot of rocks, and almost the entire thing was covered with rocks and coarse grain. But there were also two smoother patches of regolith that I noticed, which were interesting because the rest of the asteroid was covered with rock and coarse grain. Yeah. So like I said, there were around 7 to 8 distinct boulders, and it was covered mainly with rock and coarse grain, with two smooth patches of regolith. I said that the larger rocks and boulders were likely older because they originated from disruptions of the asteroid's parent bodies. So I thought that the rocks and boulders were deposited on the surface from the Brazil nut effect, which is when impacts bring up features, larger features from underneath the surface, and they bring them to the surface. And then I also figured that space weathering played a pretty big role because it's always constantly affecting and changing the regolith. That's why you can see the two distinct smoother and rockier patches. So therefore I thought that the regolith areas were younger, but that they're always constantly changing, and the boulders were also could be a product of that.
So I decided to add a little context slide of mine. On the right, you can see not an image, a GIF of my asteroid Vesta in its rotation, and on the left, you can see the spacecraft that visited it and another asteroid that it visited called Ceres. The spacecraft itself was called Dawn. Yeah. So there wasn't really a scale factor, so it was difficult to nail down what was simple and complex. But what was easy to nail down was at the top right, the grooving, which was sticking out like a sore thumb to me. Although I do feel like that after you mentioned how I got the scale factoring wrong, I might be wrong about this image also having complex craters because they seem a little small to me in retrospect now, but you can't really edit a slide during the presentation. So could you go to the next slide? So again, three features: simple craters, complex craters, and grooving. The complex craters, like I said earlier, were most likely older relatively than the simple craters. And the grooving, I said, was likely caused by an impact similar to what would be causing all the cratering, because it seemed to be just as wide in diameter as all the other craters. And basically how that forms is that it comes in at an angle. So instead of causing a direct crater, it gives the asteroid more of a haircut and gets some of its surface to split open, which is what causes the grooving.
So this one is my image. It's pretty different because it seems a lot more close up than the other two. So you could go to the next slide. So I picked out the largest features I could see. I saw large boulders, medium boulders, and then there were areas with like smaller rocks and a lot of fine dust, regolith almost. So go to the next slide. So like I said before, the image shows a lot of large boulders, and there's not a lot of cratering visible, but through further research, I found out that this image is likely arrows, and you can see through the full image that there are craters on arrows. And based on one of the readings, Eros is located in the inner asteroid belt and orbits the sun, and it has features similar to Itokawa, the first image. Like Itokawa, Eros is a type S or stony asteroid, which is supported by the features in the image. And so a little bit more about how they formed. The presence of large boulders on the surface could be due to the Brazil nut effect, like Zara mentioned earlier. The way I think of it was shaking caused by an impact with another external object caused the largest particles to make their way to the surface, causing the large boulders. And originally, I thought that the smaller or finer dust particles could have been the result of previous asteroid collisions during our solar system's formation that broke down the larger particles. But since then, I've learned that there's continuous space weathering that caused the formation of a layer of fine dust. That's more than likely the explanation, because asteroids are constantly changing during their orbit due to outside factors like micro debris from other bodies and solar winds. Those sorts of events can affect the way asteroids appear.
That's the last slide.
Yeah, that's the last slide.
Okay. Okay. So just one comment. So you're talking about solar wind affecting an asteroid's appearance, and that comes down to the idea of that darkening. So they can kind of be darkened, or their albedo, their brightness, can be changed from that. So that's an example. Yeah. So this particular image is this last image here. If you can go up to it. So this is from Eros. You're right. And yeah, in these images, I didn't include a scale bar, partly because in the first two images, it wouldn't be useful because the scale would change depending on what part of the image you're looking at, and because you see that where they are around the curvature, that's going to change it. So that's mostly why I didn't do that. So just for sense of scale, the larger boulders in this image are about the size of a house. So this area is covering kind of like a neighborhood, kind of an area, subdivision, if you will. But yeah, on Eros, like Itokawa, in the very first image, I did Itokawa, and then Vesta in the second image. So asteroids like Eros and Itokawa, experience this thing called the Brazil nut effect, where so they get bombarded, right? They're getting hit by particles. They're just not as big as anymore as they used to be, but it isn't enough to shake them up. And because these are asteroids that are probably the result of several different bodies coming together to form one larger one, there's all kind of a mixture of sizes of boulders and dust and everything. So every time they get shook by an impact, stuff starts to sort itself out like a cereal box. Actually, just got to the bottom of our Cheerios box the other morning, and I thought of this. Had a bunch of powder at the bottom of the box. So these are pretty straightforward images to discuss, and a whole lot to discuss. Let's go to the Vesta image.
Okay. Is that this one?
Yeah. So I don't remember. Did you talk about that the groove that you pointed out there near the top, where the shadow starts to creep in? What that's a result of?
That was a result of a impactor hitting it at an angle so that it really just scraped off of the surface rather than causing an actual crater.
Okay, I see what you're saying. Okay, so that groove, if you can actually see it, or it's kind of hard to see, if you go further up in the picture where it starts to get in those shadows, you see more of them. So these are actually concentric grooves or whatever, and it's kind of like a rippling from a very large impact that actually hits head on. with Vesta at some point in the past. And that rippling effect you can actually see in other craters or around other craters and other objects on the solar system. And I'm not talking about the big peak ring and complex craters. It's just where the ground actually was undulating and waving from the impact. And you can even see it at Meteor Crater, which is in northern Arizona, outside of Flagstaff. If you're standing on the rim of Meteor Crater and you look out on the plain around it, you can actually see the ground where it kind of has little waves going in it, even like 50,000 years later with erosion and weathering, you can still see it, which is pretty cool. And I, just for fun, I've never done this before, but I went and I looked up to see what the transition diameter is for Vesta. And from a paper done a decade ago, it's an abstract for a conference, this is saying it's about 30 kilometers is a transition diameter for Vesta. So transition diameters are, here's a math term, inversely proportional to the gravity field of an object. So the larger gravity field, the more gravity, right, that an object has, the smaller, the lower that transition diameter is, because what basically is happening is the stronger the gravity, when you get a crater and you get those bowl-shaped walls, gravity starts pulling that stuff down, right? So the stronger the gravitational field, the smaller those can be before it starts to pull them down. It also depends on just the strength of the material on the surface. So for example, on the moon, the Highland material, I don't know which is which, could be stronger or weaker than the Mare material. I'm actually not really sure which is which, or if there is much of a difference. But on Earth, you have sedimentary rocks, you have igneous rock, right? You have different types of rock that'll have different kinds of strengths. And so that would really affect transition diameters on Earth. All right. Well, good job. That's all I've really got. I never really have much for the asteroids images because they're pretty straightforward, like I said. Okay. So in a combo here, yeah, actually you can kind of tell where there was like two circles that kind of came together, like kind of right there at that neck. Kind of looks like a bowling pin with the top of it bent over to the side. And one thing I'll point out on the left side of that image, that big boulder looks like it's just kind of hanging on there on the end. I don't remember the size of that, but there was about a decade ago, February of 2013, there was an asteroid that entered the Earth's atmosphere and exploded over Russia, over a city called Chelyabinsk. Created what was called an airburst. So it didn't hit the ground, but it, like I said, exploded in the atmosphere, and then all that force then just went down to the ground and actually damaged a lot of buildings, knocked people over. You can see videos of it. You can see dash cam videos of the thing coming in through the sky, and it was like in the morning, so it's pretty bright considering the sun was already up. And they did find recovered pieces of the asteroid, little, small fragments of it. But that caused a lot of damage. So you don't necessarily have to have an asteroid hitting the surface to cause damage. They can explode in the atmosphere. This still cause a lot of damage on the ground. So, anywho. All right. So thank you again. We've gotten past kind of the first, well, it's not really a gate, so to speak. It's just the first task. Got through that, so that's good. So from here, I guess you've already been talking to your advisor, Dr. Ahrens, at NASA Goddard, and she's brought along Dr. Lalachi, who he was an advisor a few years ago, but his team wound up withdrawing. So I don't think he really kind of got the full experience, but that's okay. So that's cool if he's going to hang out with you all, or with Dr. Ahrens and help you all. That'll be good. So like I said, you're not going to really hear from me much after this. In fact, probably not at all. Until it comes time for your presentations later in the year. So you'll be just working with Ms. Heimowitz and your advisors. Have you like narrowed down a topic, or at least Are you thinking lunar or asteroid, and if so, is it a more specific topic than that? Have you thought much about it?
We're still kind of in debate of what to